Hi, my name is Pintuan Huang, and I'm here to present the Academia Sinica systems of speech recognition and speaker diarization for the CHiME 6 challenge. In this presentation, we'll start with the multi-array ASR task and then the diarization plus ASR task. For each task, we will present our contributions and results. For track 1, the main difference between our proposed system and the baseline system is threefold. First, we applied WPE, GSS, and BF to all the connect data in the training base. Second, the alignment and lattice for the connect training data were copied from the warn data. Third, we used 4 other kinds of acoustic models, including our proposed DCAE and FEE. Here are the results for track 1. As you can see, most of our individual acoustic models, especially TDNF and DCAEU, outperform the baseline. And after combining the 5 acoustic models using NBEST Rover, we achieved relative word error rate reductions of 7.8% and 8.8% for the development and evaluation sets respectively. Next is the flow chart of our data preparation. Starting with the upper left corner, this part is the same as the baseline, where we use both left and right channels of the warn microphone data and combine them with the simulated reverberant speech using IRS and point source noises to form our warn training set. Next, looking at the top right corner. In the baseline system, the connect set consists of 400,000 utterances randomly selected from all connect channels without any enhancement. Instead of that, our connect set is a combination of all the first channel utterances and the corresponding enhanced utterances. The enhanced utterances were created by passing all channels with time annotations to the front end of weighted prediction error, guided source separation, and beamforming. Next, we use the warn training set and the connect training set to train our GNN. Afterwards, we performed phone alignment on the warn set with the GNN and applied data cleanup. The cleanup procedure is the same as the baseline. Now to train the neural network-based acoustic models, we then created the alignment and lattice for the complete training set by copying the alignment of the corresponding left channel in the warn set, which is the alignment expansion block indicated in the flowchart. Now to train the NN-based acoustic models, the training set was augmented by speed and volume perturbation. All the acoustic models were trained on the chain structure using the Keldy toolkit, with the input feature vector consisting of 40-dimension MFCCs and 100-dimension I vectors. For our system, we used 5 acoustic models, namely TDNF, residual bio-STM, DCAEB, DCAEU, and FEMU. As most people are familiar with TDNF and residual bio-STM, we won't go into the detail here. We will only explain the structures of our proposed models, DCAE and FEE. Here are the structures of our proposed acoustic models. Beginning with the one on the left, DCAE is short for Discriminative Autoencoder. It attempts to separate the input feature vector into the phonetic part, that is the P code, and the residual part, that is the R code, in the embedding space. In this challenge, we not only corrected several minor mistakes in our previous implementation, but also upgraded its structure from NA3 to chain. In this way, the lattice-free MMI criterion, the cross-entropy loss, and the mean squared error can be optimized simultaneously by Keldy's training procedures. This model is called DCAE-B. As for DCAE-U, skip connections were added between the encoder and decoder layers. Next, for the feature-enhanced acoustic model, which is denoted as FEMU, there are also two kinds of output layers. One is the phone state score for the lattice-free MMI criterion and the cross-entropy loss, and the other is the generated acoustic features. The acoustic features generated by the feature-enhanced networks are expected to be close to the corresponding warn features during training. We assume that the warn set is clean, so that the feature-enhanced networks can play a role in further enhancing the connect features. Now moving on to track 2. The main difference between our proposed system and the baseline system is also threefold. First, all channels of the connect data were used instead of one specific connect. Second, we developed a new training scheme for speaker representation using speaker change information and CNN-based ResNet 34. Third, we performed resegmentation with VB diarization. For the result, as you can see, all of our individual acoustic models, especially DCAE-U, outperform the baseline. And after combining the 5 acoustic models using NBEST Rover, we achieved relative word error rate reductions of 11.7% and 8.2% for the development and evaluation sets respectively. In this table, we use the acoustic model of the baseline system with our diarization method. You can see that our diarization method outperforms the baseline in terms of both DER and JER. It is also clear that better diarization leads to lower word error rates. Now for the front-end processing of our diarization system, we mostly followed the baseline program, except that we used all channels in the connect data instead of one. Some failures occurred for unknown reasons when beamformit was executed on all channels of all connects. Therefore, we tried all possible combinations of channels and selected the set that contains the most compatible channels. Now for the speaker modeling. The main weakness of most speaker models might be the incompetence to discriminate short duration segments and the ineffectiveness to extract a reliable speaker embedding when a segment contains more than one speaker. Speaker representation is crucial to speaker diarization, especially when segment clustering is performed. Therefore, we propose a new training scheme to develop speaker representations by randomly augmenting the training data with segments that contain more than one speaker. That is, we attempt to produce one or more speaker change in each mini-batch while training. A soft label was applied to each segment based on the speaker occupation ratio, and the standard cross-entropy loss was used. Take this figure for example. Traditionally, the ground truths of training samples are one-hot vectors, like the ones shown on the left. In our proposed system, the ground truths can be 38580 or 283838, as shown on the figure on the right. To build a speaker model, we employ the CNN-based ResNet 34 architecture. The initial speaker label for each segment was given through clustering the speaker embeddings. Resegmentation was subsequently performed with VB diarization. To conclude, in track 1, we evaluated newly proposed acoustic models, naming DCAE and FEE. From the results, we can see that DCAE outperforms TDNF. As for FEE, It will need some more modifications and fine-tuning in the future. In track 2, our proposed speaker modeling method was proved useful for speaker diarization and downstream ASR. And that's the end of our presentation. Thank you so much.